Hi there, welcome back to A Slice of Physics. We're now ready to tackle another example to do with electric fields, and this time we're going to look at figuring out the net electric field at a point from two charges. So we'll have to use some vector addition to figure out the net field from two separate charges. Alright, here's the specific question we're looking to tackle now. We want to determine the net electric field at the origin from two negative 40 nanocoulomb charges, one of which is placed 3 centimeters to the right of the origin and the other is placed 2 centimeters above the origin. As always, our solution steps are listed here, which in this case would be sketching the situation, considering each charge separately to determine the field at the origin from charge A and charge B. So let's call these charges A and B. And once we do that, we want to determine the net electric field at the origin as the vector sum of the above electric fields for each charge. Let's get started with the diagram. Let's say my origin is over here. Charge A sits over here. It's minus 40 nanocoulomb and sits 3 centimeters to the right of the origin. So this is 3 centimeters. And charge B, which is also minus 40 nanocoulombs, sits 2 centimeters above the origin. So let me show charge B over here. And this distance here is 2 centimeters. Okay, there's our picture. And now we want to consider the charges separately. So let's consider charge A first and figure out the electric field at the origin from charge A. Now note again that there is no charge at the origin. There doesn't have to be a charge at a point where there is an electric field from charges near it. The equation for electric field over here is E equals K, the constant, Q, the absolute value of the charge, divided by the square of the distance. That only gives me the magnitude of E, and we'll get the direction as the next step. So in this case, putting in the numbers, this is 9.0 times 10 to the 9 for K, and for the charge Q, since I only need the absolute value, I can drop the negative sign, so it's 40 times 10 to the negative 9 coulombs, divided by square of the distance, and I'll convert the distance to meters because K is given to me in Newton meters squared, so for the units to cancel, I have to put the distance in meters. So this distance of 3 centimeters becomes 0.03 meters, and I square that. The rest is done by your calculator, and you will get 400,000 or 4.0 times 10 to the 5 Newton per coulomb. That would be the magnitude of the electric field from charge A at the origin. Now we need to figure out the direction. We know that the direction of electric field, and it's given over here, is away from the charge if the charge is positive, and toward the charge at the point of interest if the charge is negative. In this case, our charge is negative, so the electric field will act at the origin toward that charge A, so it's directly acting to the right. So this would be E sub A, which is the electric field of charge A at the origin. Alright, we know its magnitude, we know its direction, so we're done with the electric field at the origin from charge A. Now we move on to charge B, and let me do that over here. Same equation, I've got E sub B, the magnitude of it will be K, which is 9.0 times 10 to the 9, times the absolute value of the charge, which again is 40 times 10 to the negative 9, divided by the square of its distance from the origin. Since our point of interest is still the origin, I care about the distance of B from the origin, which is given to us as 2 centimeters. Once again, converting it to meters, it's 0.02 meters, and I got to square that for the equation. And when you put that into your calculator, you'll get 900,000 or 9.0 times 10 to the 5 Newton per coulomb. That's the magnitude. For direction, I go back to the picture and I remind myself that because charge B is negative, the field at the origin will be acting toward that charge. So it'll be acting straight up. And since it's 900,000 instead of 400,000, this is going to be more than twice as long as EA. So let me just show it like that. So this is EB. So that completes step 2. I've got the electric field magnitude and direction from charge A, electric field magnitude and direction from charge B. The last step was to figure out the net electric field at the origin which would simply be the vector sum of EA and EB. So for the net electric field, I have E net at the origin is simply EA plus EB, not just adding the numbers, but reminding ourselves that these are all vectors. I got to add them as vectors. To add them as vectors, I've got to slide the tail of EA to the tip of EB, or the other way around. And then the final answer would be from the original tail to the final tip. So this diagonal line would be E net, the net electric field at the origin from charges A and B. All right, how do we determine that? So given that we got a two-dimensional situation over here, I've got EB that's vertical, EA that's horizontal, and E net, which is diagonal over here. I got to use trigonometry and Pythagorean theorem to get the magnitude of E net and the direction of E net. To get the magnitude, that's simply the length of this diagonal line, and since that's the hypotenuse of this right angle triangle, I have E net magnitude is simply the square root of the sum of the squares of the other two sides. So EA squared plus EB squared. So that would be 4.0 times 10 to the 5 squared plus 9.0 times 10 to the 5 squared again. And then you take the square root of the whole thing, which your calculator will tell you is 9.849, or since we have only two significant digits, 9.8 times 10 to the 5 Newton per Coulomb. So that's the answer to the magnitude part of the net electric field. To give a direction, because this is a slanting line, I can't just use a sign to give the direction. This is not along either axis, so I got to come up with an angle to specify its direction. So let's make this angle what defines that vector. So I'm going to call this angle theta. And completing this right triangle over here, I've got the opposite side to theta is the same as EB. The adjacent side to theta is EA. So using my SOHCAHTOAs, in this case TOA is the relevant one since I know the opposite and the adjacent, I get tangent of theta equals opposite of it, which is EB, divided by adjacent of it, which is EA, which is 9.0 times 10 to the 5 divided by 4.0 times 10 to the 5. The 10 to the 5s will cancel, and 9 divided by 4 is simply 2.25. And to get theta, I got to take tangent inverse of that number. So theta is simply tangent inverse of 2.25, which your calculator will tell you is 66.0 or 66 degrees. So there we have it. The net electric field at the origin from charges A and B is given by its magnitude, which is over here, of 9.8 times 10 to the 5 Newton per Coulomb, and its direction, which is 66 degrees above the positive x-axis as shown in the diagram. So in this video, we saw how to determine the net electric field at a point from two charges, and we did that by first treating each charge separately and determining the electric field, and then adding the two individual fields as vectors to get the net electric field, and that needed some trigonometry. Thanks for watching.